We are now getting ready to listen to Kees Cook. He's here to tell us about control flow integrity in the Linux kernel. So please help me in welcoming him here today.
Cool. Thank you. I'm just, if anyone wants to follow along with the slides, I've got the URL to grabbing the PDF there. I have a couple links scattered in there, and there's illustrations if you want to go back through that. Anyway, yeah. Before I begin, I'd like to acknowledge that we meet today on the traditional lands of the Ugimba people, and I pay my respects to their elders, past and present, and leaders emerging. For anyone who wants to learn more, I found these two links very helpful starting points. So the agenda today, just sort of covering the slides and the information I want to get through, and sort of what is this I'm talking about at all, and why does anyone care? Looking at the Clang compiler in particular and how it implements CFI. What Android phones are doing in this space, especially the more recent Pixel phones. Tricky corners that we had in dealing with CFI generally and specific to the kernel. Where things are in upstreaming, which of course leads us to doing it yourself. It doesn't matter if it's in a corner somewhere. I want to make sure everybody can do this as easily as possible. So what is kernel control flow integrity and why should we care about it? I think of it as an attack surface or maybe an exploit surface reduction where most kernel compromises are about gaining execution control, usually from a write primitive. You have some flaw that gives you the ability to write into kernel memory and make changes there. But of course, not all flaws are created equal. You know, some flaws let you overwrite only a certain number of bytes into some structure, or only let you write a single zero somewhere, or let you only write a fixed string of bytes. You know, you don't have control over what you're writing, just where it's happening. But given that, the worst case is the write anything, anywhere, at any time. But those are relatively rare. So if we look at sort of the historical attack model was, well, as an attacker, I'll just change the kernel code itself. You know, I'll just write directly to what's running. This was used by ancient rootkits and like antivirus software, which were indistinguishable from rootkits. But most importantly, as an attacker, the thing you wanted to look for was you needed memory permissions that were both executable, in other words, the CPU would happily run it, and writable, so that you could change it with just the write flaw, the arbitrary write, without any other code that you were running. So starting with a little diagram of memory space. If you're executing from user space, obviously you can do whatever you want to user space memory. You can change permissions, do anything. So as far as writable and executable code, you can touch all of user space. But you can't touch the kernel memory. But once you've found that kernel flaw and you can write from the kernel, and there were open permissions and everything, you could just write to anywhere in the entire system. So eventually we get the NX bit and you say, well, you can't actually execute data portions of the kernel, but you can execute the text and the modules of the kernel. And then we said, well, how about making that read-only? So like, okay, fine. So executing from the kernel, what's writable and executable is still all of user space. And so finally we said, all right, we also have SMEP on x86 or PXN on ARM. And suddenly that entire attack method is just gone. You can't write to anything that's both writable and executable. So that's sort of the last century of defenses. So you go, okay, as an attacker, what do? I can't write to the kernel code directly. Maybe I can call into the kernel and I can overwrite function pointers that exist in memory. The most common of these is writing to the stack, and you can manipulate the return pointers, and that's the whole ROP universe of attacks. So in that situation, the target that you're interested in is writable and contains function pointers. And this works with specifically hijacking indirect function calls. Which begs the question, what is an indirect function call? Here's a direct function call. In blue, I've sort of got the, we'll build on this example, the C of something calling another function, and there's the other function, like the do simple. And if you look at the assembly code, it just says call this hard-coded address. As an attacker, you can't change that. That's in the text. You know, that's not writable. You cannot mess with a direct function call anymore. But if, instead of doing a direct call, you have a saved function pointer, like there's an array of various functions you may want to call, and you do look up some index, and you extract which function you want to call, and then you call that function, and you look at the assembly, you're actually calling into a location held by a register. And fundamentally, if you can hijack, as an attacker, where the function pointers are, you know, if you can find where they're written, and change the contents, you can call anywhere, which is a lot of control. And to add the terminology, this is considered the forward edge of your function. And you look at the targets you've got the heap, where these function, like in this example, where is a table of function pointers. And you've also got the stack, where you're potentially storing things temporarily, and as we'll see, there is the backward edge as you return, and that's also stack. On the stack, you've got the return address and all the other things that have been allocated there. So if an attacker can write to stack, you can get it on the way back out. This is, like I mentioned earlier, the return-oriented programming style. So going back to our memory layout, it says, well, OK, what contains writable function pointers? Again, if you're writing from user space, you can write to all of user space. You can't touch the kernel. You're going through a kernel flaw. You say, OK, I can write to all of user space from the kernel, and I can write to the heap, and I can write to the stack. And we're not going to get to the point where we have a read-only stack, because that makes it very hard to use in normal programming. But as we added SMAP and PAN, user space suddenly became out of bounds. And now that's a much more narrow attack surface. You have a lot less control as an attacker on what you can manipulate. So we're down to just the heap and stack. And so the question is, as an attacker, what can you call from the kernel if you have access to one of these function pointers, either through forward edge or through backward edge? You can basically jump to any byte in executable memory in the kernel, which is a gigantic exploitation surface. So control flow integrity wants to, and I'm just going to read it here, we want to ensure that the indirect calls can only reach sort of an expected subset of the functions that are in the kernel, and that any return pointers that are saved on the stack are unchanged since we called into a function and came back. And that's basically why we're here and what we care about. For forward edge protection, and this is generally speaking, we want to validate the indirect function pointers in some way. How do we figure out what the control flow of the kernel is, or any program? And a lot of research went into this, and ultimately where we are now is you look at the function prototype as a best uniqueness idea. You say, you look at the return type and all of the argument types, and that's the type of function you're dealing with. So in this example, it doesn't matter what it's called, but they both return int, and they both take unsigned long and a struct file pointer. So at any place where that type is called, you could call any of those functions with a matching prototype. You could not, in the other example, when they take the same argument but they return different things, these get put into a different bucket when we're trying to figure out how to validate things. The hardware solutions, because we're mostly covering a software solution here, but the hardware solutions on this in coming future CPUs are not great. They have really poor granularity. They basically say the only place as an attacker you can jump is to the start of a function. Any function. So it's a smaller subset, but it's still any function anywhere in the kernel, which is probably what you were already going to be doing as an attacker. So to reuse this from before, you have a write, and you have a couple functions that have the same type. Now instead of every byte in the entire text, you can only call into matching function prototypes, which narrows what you can get at quite a bit. So the question is, how do we do this? In Clang, one thing that's required is link time optimization, which effectively says it gives the linker and the compiler visibility across the entire code base at once. Normally, you're sort of building .o files individually, and you sort of link them all together, and you don't care as long as the symbols match up, things are cool. LTO says, oh, I'm going to look at all of the functions that are going into the kernel at once, and then it can evaluate, OK, here is a call site that does these types of functions. Let me find all of those function types, and I can collect a list of them so that I can check at every call site that it's only part of this list, et cetera. One weirdness is that symbols start to get a little strange under LTO, but it's OK. So anyway, collect it into jump tables is what I was getting at. And the thing, this sort of high-level description of CFI is talked about in, if you go look at Clang's documentation, that gets described. But I really wanted to see what this looked like at the assembly level. Like, what are the actual bits? How is it being validated? This is a nice theoretical idea, but how are we actually doing it? So I want to compare and sort of build up what this looks like. This was sort of the original assembly output from C. We've got two functions, do simple, do fancy. They don't do much, and then return. And we've got the action launcher that's going to go look up the index and call an indirect function through this register. And right now, this is exploitable as far as being able to call anywhere into the address space, because there's no validation on the contents of RAX. If you add a whole mess of options to Clang, you get the jump table gets added, and then a bunch of validation gets added. And I'm going to step through each of these pieces so you can see what's actually happening here. So the first step is we're going to actually take the literal value of the address of this jump table, the starting address, and load it into ECX. We're going to subtract it from a copy of the function pointer we want to be calling. So now we should have an offset from this jump table. And we say, OK, we're going to rotate it right. And notice this is not a shift. This is a rotate. We're effectively dividing by 8. So we want to get the index within this table. And we rotate because if our subtraction was way off, we're way far away, we end up with a whole mess of bits in the high bits, and things go very badly in a later comparison. And then we're checking, are we at index 0 or 1? We're looking for a jump above on the next one. So if it's 2 or higher, or there's a whole mess of high bits set because the rotate went weird, this will fail. And we jump to an undefined instruction, and the kernel freaks out and stops things from continuing. And what you can see here is what we've done is the function just calls into this jump table and jumps to the actual function. So everything's fine. There's just a little bit of indirection that happens, which has sometimes a measurable performance hit, but it's not terrible compared to what you get. As an aside, the insane symbols that got added for the jump tables, you can actually put through the demangler, but you have to extract the type ID and the global address piece from it to actually find out what in the world, what type is this that was actually chosen and encoded here. So you can actually stuff this through LLVMs, C++ filt. GCCs has no idea what a type info mangling is, but the LLVM tool can actually tell you what this is. So this is the int struct foo pointer type that we saw in the example. Now, this is what Clang has done. It works well enough. The question is, are there some better implementation ideas we can do here? Instead of jump tables and a whole area that I haven't covered at all with dynamic shared objects, they're somewhat slow. Another CFI implementation in Pax Team's wrap actually adds hash checks immediately before functions and immediately after or before return locations, and it'll read out the kernel text to check those hashes. It's a clever idea, but it's not actually compatible with the future of execute-only memory. In other words, memory that you cannot read, and that's going to be a problem in the future if we end up marking the kernel as not readable. You can execute it, but you can't read it, which means you can't, dump it and look for gadgets and do whatever else to sort of stop information leaks. Another issue is that, as it turns out, the kernel has a lot of functions that return void and take void. So that is a gigantic table of all the possible functions that are in there. It's, I think it was like 300 hex in whatever I was looking at. And the Android kernel team actually took a look at this to figure out what is the actual benefit here? How far have we reduced the attack surface that we're getting? So they looked at, for every call site, how many possible targets do we have? So the most, like over half of the indirect call sites have fewer than 5 possible functions that can be called at any given location. The problem is that there's a long tail, and way out at the end is stuff that calls a void that takes void. And so there's, if you, as an attacker, can get at one of those functions, you sort of have a lot of functions you can choose from to perform your attack. So I'll go back up to mention the CFI pass and LLVM. This isn't public yet, but I keep harassing him to release this. It actually does a secondary analysis of the call chains and tries to figure out smaller subsets beyond just the function prototype information. It says, well, yes, you call a void function, but you only ever call 5 of them. So we can actually create a secondary, smaller sets of jump tables. And that, I think, would make a nice improvement in this, just to get rid of the sort of scary tail at the end of this graph. So that was forward, but we have backward edge still. We have the return. And the idea here is we have to have some sort of trusted stack. Like we can actually depend on it to contain our return addresses. You could have, the software version is you could have a dedicated register for a separate space in memory that contains only the return addresses, and that's considered the shadow call stack. But as it's turning out, this is looking like it's going to be done a lot better in hardware. Intel's CET and ARM64's pointer authentication look like they're very fine, very high granularity, and should be pretty decent in future hardware. But since we're not there yet, we're going to look at the software versions of this. Unfortunately, the x86 implementation of this was slow and had race conditions, so it was removed from Clang. So there isn't a very good solution on x86 for backward edge CFI protection in software. ARM64 is a little bit better. You can reserve a single register that never gets spilled out to the stack. You avoid having memory exposure risks to x18, which would, you have a separate stack. And you only ever put your return addresses there. And I'll get to showing what that looks like. Now, anyone looking really closely here will see that the return address actually shows up in the traditional stack pointer stack and in the x18 stack. And this is mainly to not break the backtrace unwinders who are expecting to find all the variables and all the stack, all the return addresses and build everything up. But as it happens, the copy that's in there just gets ignored in normal operation, and I can show that here. So if you're building with these arguments on ARM64, you effectively end up with 2 stack pointer registers. The before is over here. The x30 register is effectively the return address that you want. So in the beginning, we save x29 and x30 to wherever in using the stack pointer as an offset. And before we return, we restore x30 out of the stack and then do a return, which effectively jumps to x30. If we enable the shadow call stack, The first thing we do is actually store our return address, x30, into the x18 stack. And on return, we expressly bring it back in. And we ignore the one that we pulled right before that. So it just gets ignored, and we stick only with that stack. This, however, of course, means that you need to keep the location of your shadow stacks secret. So it's not a perfect solution. And I think the hardware is going to look a lot better. On Intel, this is going to happen implicitly. There's no actual changes to the assembly. Like, your runtime needs to have set up the new memory location, but calls and returns will actually operate on that shadow stack automatically. And that shadow stack is effectively read-only, except for the implicit writes that are happening through call and return. So it seems like a relatively clean solution for the future. On ARM, the future will have return signed return addresses. You can sign other types of pointers as well. And it looks really similar to the software solution. We sort of sign the stack pointer before we store it, and then right before, like, we've pulled stuff out of stack, but we haven't used anything. We haven't used the x30 yet. And then we say, hey, where I just read from, is that stack pointer still correct? And if it isn't, it blows up at that address or at that instruction. And if it's OK, we return. And the arguments for that exist right now. Getting hardware, I think, is more tricky for this. But I think the latest QEMU supports this for ARM64. So where are we in the real world for this? The Pixel phones actually have this. Sami Tolvanen and others have done a huge amount of work to enable LTO and CFI and the shadow call stack in Android and in the upstream kernels. The first version, so Forward Edge, was added in Q3 of 2018 in the Pixel 3 phones. And when the Pixel 4 came out, that added the backward edge protection and also added it to the Pixel 3 phones. So it was just sort of took a while to get it developed and finished and integrated, but it was added, like that feature was added to the older phones as well. And what's good about this is the work that was done is for the Android common kernel as well as the device, the Pixel device kernels. So if you look through the Android compatibility definition document, the CDD basically is telling vendors, if you're building Android going forward, you really need to have this enabled. So the idea is that the entire ecosystem for Android phones will have this going in the future. Traditionally, the strongly recommended stuff in the CDD, the next year it becomes required. So it gives a little bit of leeway to vendors who are not ready for it yet. But my expectation is that this will become a requirement for the entire Android ecosystem moving forward. There were a lot of various problems that got encountered. The first one was adding LTO. As it turns out, trying to link the entire, hold the entire kernel in memory while you're doing a link and analysis of all of the functions everywhere is gigantic. It takes a lot of memory and a lot of CPU, and it was like massive linking times, and that was a problem. Luckily, there was another LTO type in Clang called thin LTO, which did a lot less work and used less memory and less CPU. It had a lot of strange little bugs that needed to be fixed along the way, but now the linking time is not egregious, it's just slow. Assembly code. So the kernel defines all kinds of implementations of various things in assembly. For example, like crypto functions or hash functions. And there's all these indirect tables for calling into all of these assembly functions. But CFI, of course, is in the C lang compiler, not in the assembler. So there were no jump tables being generated for assembly code. So some indirect function would go, cool, I'm going to go use like the SSE3 accelerated SHA-1 and would jump and not find it in the jump table and freak out. So the idea was you have the C compiler generate table entries for anything it finds that it might, that has been declared as callable. And then later, when you're linking stuff together, everything's OK, and you can call into those functions. That did require rearranging quite a bit of how Clang was generating those jump tables. But I added that argument, which is what I used earlier in the example, just so we had the same type of output. Relative addresses would calculate the address of the function, not the jump table entry. So the solution was just to turn that off, since these the exception tables are all effectively hard-coded anyway. Linker aliases were just yet another way of confusing the C compiler, because that's not part of the C portion of implementing CFI, but you could reconfuse it with a different alias and satisfy it. And then another fun one was KPTI, the kernel page table isolation. To deal with Meltdown, the solution was, when you're in user space, you leave a very, very small entry stub mapped in the kernel memory space, and you leave all the rest of the kernel unmapped. And that entry stub was effectively would check some things and then re-enable the mapping for the rest of the kernel. However, there's a lot of indirect function calls in there, and it would attempt to go jump into the jump tables that were not part of the entry stub. They were part of the unmapped portion of the kernel. So it's like, OK, well, we have to map both the entry stub and the jump tables, and then everything's fine again. That was adorable. Let's see. So upstreaming status. Crossing my fingers, I think of Clang as done. There's a lot of bugs related to various little corner cases and everything just with building the Linux kernel with Clang generally, and that's tracked the Clang Built Linux GitHub here. Nick DeSaulnier has been doing and organizing a lot of other people to help with all kinds of things in this area, not just specific to Clang and CFI, or not specific to CFI and Clang, but with Clang generally speaking. The big amount of work here that made this possible at all for x86 was actually adding ASM goto support, which is, again, unrelated to Clang, but actually makes this possible under x86, which is sort of my view is getting CFI working for as wide a portion of the Linux ecosystem as we can possibly manage. And as it turns out, x86 has a rather large install base. So on the kernel side, the shadow call stack support is pretty separable, and it's expected to land in the 5.6 merge window. It doesn't have a lot of prerequisites like LTO and all these other things. Getting CFI working requires that the kernel have correct function prototypes everywhere. There's a lot of places where they go, well, I don't know what function I'm about to be calling. I'll just call it void pointer, and we're good. Well, that'll fail because the CFI is expecting to only look at a void when you're calling into something else, and it's in a different jump table. So going through the builds and finding all the function casts, luckily the compiler has some warnings that can help us with that. So I think most of those are tracked down. I resent one outstanding patch this morning. So hopefully that's like getting the kernel code ready for CFI is nearly done. The LTO stuff is mostly changes to the build scripts, because in LTO, your generated .o file is no longer actually binary code. It's like LLVM intermediate representation code, and binutils has no idea what to do with that. It says, I can't do that. I can't look at this. So there were a lot of places in the build system that wanted to examine an object code at some point, and so you have to figure ways around that or replace it with LLVM tools instead. But that's all working. We just need to get it into upstream. And there have been some questions on like variable lifetime visibility under LTO, maybe doing things because the C standard memory model and the Linux kernel memory model do not necessarily agree on certain things. And there's a lot of very small details here that I'm hoping are settled now. We'll see when this gets sent again. And then there's actually CFI itself. Like we can't do anything with that patch series until LTO is landed. And I'm hoping that will be entirely uncontroversial, which is never true, but I can hope. And that one should land easily, and again, with all the prerequisites done, it should be very fast and get in. So I'm hoping maybe 5.7, 5.8, it would be nice. So that comes down to how do you do this yourself? All the outstanding patches are in Sammy's GitHub tree. It's, like I said, it's not huge. It's like, I can't add quickly. So 50 and, yeah, anyway, so it's like 50 patches. They're relatively straightforward. And the thing to keep in mind is that the kernel build system now very much wants to know what compiler you're using. So much so that even when you're doing kconfig setups, like make def config or make menu config, you need to remind it that, oh no, I'm actually going to be building with Clang and linking with LLD. Because if you do a make menu config, it goes and looks around and says, oh, it's GCC, cool, you can't do CFI. And then everything gets confused. So always pass in the parameters for the compiler and linker you want. And then those are all the configs to turn on. You're turning on LTO in a general sense, and then thin LTO because you don't want to wait for an hour. And then turning off LTO none because turning on LTO Clang doesn't turn off LTO none if you use scripts config. And then you turn on CFI for Clang and this shadow cache for dynamic objects. I did not cover that. And then the other two pieces are CFI permissive. Like if you don't want your system to fall over when there is a CFI failure, you just want a warning, and it should continue and actually call the wrong function. You'll get a large splat. I'll show you on the next slide. So permissive basically is the debugging version of this, so you can find anything that might still be missing. And then if you're building an ARM, you can add the shadow call stack to get that return protection, and then build it and enjoy. So the question is, what does this look like when it breaks? So if config CFI permissive is not set, you're going to either panic the entire system or kill the single thread, depending on which type of CFI failure and how it's set up internally. But if you have permissive, you'll get that same call trace, a rundown of where you were when the CFI freaked out, but it will just be treated as a warning and will continue and actually make that function call. Now you may notice this is only the forward edge protection. As it turns out, the shadow call stack failures are entirely unreported because it just ignores the old link register. So that, to me, seems like another area for improvement. It would be nice if we could compare what we had loaded before with what we're actually going to use. And if it differs, we should probably make some noise about it. But right now, it's just completely ignored, and you maintain whatever the return stack was without any other information happening. And that is the bulk of that. So thoughts, questions, anything else, that's where to find the PDF. And if you want to learn more about Linux kernel hardening and the self-protection project, those are URLs and email addresses if you want to reach me. This question. Anyone with a question, please run down. There is a microphone down here and up there. Sorry.
Thank you.
Excuse me.
You said we need to make x18 secretive. I don't think we have to hide x18, the shadow stack pointer. We have to randomize x18.
The bits I heard from your question was regarding the shadow call stack?
Shadow call stack, hiding the second stack. I don't think we have to make it secretive. I think we need to randomize the shadow stack.
Right. It should be difficult to discover. If you're using, the argument is -f fixed x18, and that says the compiler will never touch x18, so it'll also never get spilled, it'll never get written out during sort of normal operation, but the truth of the matter is it still does get written out during a context shift. So you've got to save it when you switch around. So it is possible to still get at that information if you have a very controlled information leak. It would be interesting to sort of move rotate the stacks around so that if you leaked during one, you wouldn't know where it was on the next syscall. I don't know. There are some improvements to be made there just because it's kind of there are some probabilistic weaknesses with the shadow call stack. Yes.
How does CFI interact with retpoline?
So it works. It just makes it harder to look at in an example. So in these examples, I actually turned off retpoline because it was jumping into the func and then jumping into the call table and then going out. So it may degrade its effectiveness a little bit. I haven't examined it closely.
So when we're in the magical future with CPUs that do this in CFI in hardware, that is going to make retpoline impossible, right?
Well, I expect us to have CPUs that are cool. We don't need retpoline before we get to the CPUs where we're doing anything beyond what we're capable of here. But there isn't a good high granularity forward edge CFI that has been proposed for hardware that I'm aware of. So the forward edge in software, I think we're going to retain for a while. Backward edge is much, much better. But forward edge, adding the branch target instruction is nice because you go down from you can go to any byte in the text to you can only go to function entries. It's like, but as an attacker, I was already just going to be calling the functions. So it doesn't really gain me too much. Now with ROP, you're doing like tail gadgets, but with like a heap overwrite, and I want to call a function and do various things, then you're like there's no benefit to that to the hardware protection. So yeah.
For the forward edge protection, are there cases where these indirect accesses could kind of come from a module and so wouldn't be available to the linker at compile time? So
I didn't cover any of the modular piece, but there is, if I'm understanding you're asking about modules and how to do that, yeah. So there is an entire system for dealing with sort of dynamically loaded modules, and that the checking for that is a little bit slower in that you have you figure out where your function is located into a module, and then you ask the module to perform that function check for you. And for the ones that are outside but potentially modular, they're actually in a different set of jump tables. So it's possible it's a little bit slower for the DSO stuff, but the DSO stuff does actually work. I just skipped over it because it's even more complex than the basic stuff. But yeah. Yes?
Do alternatives ever interact with CFI?
Do what?
The alternatives, so swapping the instructions around, Rusty's little, or is that, do they never call functions?
Yes. There's not a lot of, I do not think there were a lot of indirect calls that are also attached to alternatives. But the alternatives code, or rather some of the assembly things, really confused CFI in certain areas. And under ARM64, especially as you're switching privilege levels, it would get very, very upset. So the nice thing is on a sort of per function or even per compilation unit, you can actually disable some of that checking where you go, okay, let's look at this. It's always going to be safe here. It just has lost its mind. We should just disable CFI checking here. And it goes, cool, I'm going to just call straight to that function. We're good. So there were some of those cleanups that were necessary. But they're all in that series. Anyway, cool. Thank you very much.
Anyone left?
All right, thanks a lot.